Welcome, folks, to another PyMCon event. Today, we have the Q&A session for Ricardo, who's going to be talking about automatic probability. If you haven't seen his talk already, it was pre-recorded and published before this, so this is just the Q&A session. I'm going to kick it off with a couple questions of my own, and then we're going to be taking questions from the audience as well, both on the Discourse thread that I posted and on the Q&A. So just to warm things up, Ricardo, I know you've given an intro many times, and you've talked about your path into statistics. But since we're talking about probability, I wanted to ask you pointedly, how did you get so interested in statistical computation and probability specifically? Like, was it through studies? Was it through a PhD, a potential PhD? Like, what got you so knowledgeable and interested in this topic?
I mean, that's a tough question. I think programming with simulators. I really like simulating, like little machine learning agents, like reinforcement learning agents and sort of this. And once you start playing with simulators, you are not very far from a Bayesian-like workflow nowadays, right? Where you just define your model as like how you could have generated data. But definitely simulating was something that combined statistics, programming low level, which is I find interesting from early on, and then modeling itself, which I didn't know was a concept until a bit later. In more the Bayesian stats, it was from statistics, and I guess later on my PhD. So I started the PhD that I haven't finished. I quit. It was directly on Bayesian models of cognition.
Okay.
And that was a combination of like both simulation, because we did a lot of we had a lot of theories, based cognition based on doing simulations, and then what you get out of the simulation maybe is your inference, your Bayesian inference. And that's where I got more kind of academic interest, and where I learned Bayesian stats.
And I didn't actually know this. Where you were doing your PhD in cognition, and you were using statistical theory to do so? And your undergrad was also in statistics or something else?
So my undergrad was psychology, and then computational/behavioral neuroscience, the master's. Yeah.
Well, that explains how you know so much. So this is my next question. The title of your talk is automatic probability, and I'm somebody that didn't formally study statistics, so I'd always see folks when I was trying to learn statistics do all these. They just know the tricks, right? They would know that if you do this transformation, it becomes like a chi-square distribution. If you do this transformation, like the various distributions like fit into each other in various ways. And I think there's some clever chart somewhere that shows all the transformation, and there's like this chart seriously has like 40 distributions on it, and all the edges, like 200 edges. So something that I appreciated about PyMC, and one reason that as a practitioner was so useful to me, was this notion of automatic probability, in that like I just specified the distributions and the knowledge that I knew, just as you did in the talk, and then PyMC would auto-magically, we didn't have PyTensor at the time, but PyMC/Diana would auto-magically figure everything out, so it would both do the transforms needed for the mathematical side and also the transforms needed for sampling, but then return everything back to me in the spaces that I was used to as a practitioner. So there's the question I want to lead up to is there's on one end you have maybe naive users like when I first started out that just sort of understood the basics and my domain, but not the mathematical like underpinnings of transformations. And then you have experts that like there's some genius folks that like in their mind know every transformation. For people that are getting into statistics and let's say want to become PyMC power users, how much do they need to know about probability for you to feel like they have a good start? So I'll start with this. I feel like they at least need to know like basic things like what conditional probability means, what joint probability is, and even just the basic rules of probability. But like, where do you feel like the mode of PyMC users, like what things should they know? Because it's not all automatic, right? But what's your take?
Yeah, so before I answer your question, so you remind me a bit of frequentist statistics. So the way I learned was one of these giant diagrams, right? If you have this kind of data, this many groups, whatever, groups or sequential across individuals, then you have to apply test A, B, or C, or D.
Yes.
And one of the first things I actually like when I did computation simulation is to do your own shuffling tests or randomization tests.
Okay.
Or even bootstrap tests, which you can use basically the same 4 or 5 lines of Python code or any library code to do any test, because it's just about shuffle your data in a way that kind of erases your assumption about, if there's no group effects, you just say, let's just shuffle the labels of the groups. If we still see this large of a summary statistic, that's our p-value, whatever.
Okay.
And you could, I think you can condense 99% of, 3 semesters of frequentist statistics to 5 lines of Python code. No joke. And then you can maybe think about the nuances. And that for PyMC modeling or Bayesian modeling, ideally what we'd like is if you can define your generative code, like by just kind of chaining functions that take random draws and then doing some operations on those. And you can even, like, if you write your NumPy, like even in NumPy, if you write your model in a NumPy function or a chain of NumPy functions, if this is an accurate definition of your data generating process, that would be the ideal. You write these, now you write it in PyMC, which is a bit different, but we follow the same syntax.
Mm-hmm.
And then you should just be able to say, okay, here was my model, I observed this, right? And you do inference on all the variables that you didn't observe or have some uncertainty left. So ideally, you wouldn't need anything else than defining your data generating process. But this is like the dream, but abstraction or limitations of real developers' imagination keeps you short. I think you can do a lot by just I think it's useful, for instance, to just understand one of the basic samplers. Like if you understand just like Metropolis Hastings sampler, I think that gives you a lot of room, because you just have an idea that how is a PyMC model inferring or proposing samples from the posterior, right? Which is a magical thing. But if you just understand just Metropolis Hastings, I think you are good, because nuts is just the same thing with gradients. It's just a clever way of proposing. And then if you understand, and if you already understand your data generating process, you already understand prior predictive and potentially posterior predictive. So you know the whole workflow by just combining these 3 pieces. And then I think it's just a lot of applied examples to really sink in, because with mathematics, then you have many ways of writing the same kind of process by using different equations. And later you'll figure out that some are more efficient. Even with we trying to make it easy for users to not make mistakes, there will be always tricks where if you just parameterize it like this, it's just going to be something much faster, and it's equivalent or almost equivalent. But that's indeed some of the things we want to help users with these automatic probabilities or even automatic rewrites.
Okay, so I'm going to summarize what you said, because I think you actually said it in a way that I hadn't thought about, but I now wish I had thought about. It sounds like the 3 things are: one is the first step is if users can write down their data generating function in NumPy, that shows that they understand statistical distributions and they're problem well enough to at least define it. Now, of course, you can't perform inference in NumPy, but at least you know that your sampling is good. And then there's tricks, like you said, like if you shuffle the labels or things like that, if your distribution changes, then you maybe have some issues. But step 1 is that. Step 2 is understand basic MCMC sampling with a Metropolis Hastings algorithm. That'll get you a sense of how the samples are being drawn, and then between the data generating function and Metropolis Hastings, you'll know how your prior predictive samples are produced, and then at least your posterior samples are produced. And then the last one, actually, this is something that I'm still in awe with you guys at labs and all that can know, is there are computational tricks that if you specify your distributions certain ways, your sampling just becomes better. And for folks who don't know, this is actually when I see the folks in the labs work, this is something that I'm like really always amazed by, because a common thing they do is they take models that other people have written and then they can see the matrix and see if they rearrange things in a particular way that it becomes 10, 20, 30, 100 times faster. It's quite cool that they're able to do that. the power, I should say the power uses of PyMC, and then labs, which is a subset of the power uses of PyMC. Okay, so there's Ricardo's 3-step plan to becoming a probability master.
Yeah, definitely. Simulate data, learn Metropolis, which is pretty simple. I mean, it's maybe 10 lines of code instead of 5 to replace all the frequencies tests. And then do pursuit predictive, which is a fancy way of just simulating data, but now you put what you learned into the simulator. Yeah.
So while I'm talking, before I go into my next questions, I want to remind folks, this is your Q&A session. So if you have any questions, I'm always checking both the Discourse thread and the Zoom chat here. Please feel free to ask anything. This time is here for you. I'm going to fill the time by asking Ricardo questions, so we're not just sitting here. But I highly encourage you to literally ask anything you want. This is your moment to get some of Ricardo's genius. So Ricardo, you said something else, both in your talk and in this right now, and it's that you in the talk around, I think around minute 23, you talk about how we don't support mathematically valid use cases with Z, X, and Y, but we support use cases that are I'm sorry, we don't support it in code, but it is mathematically relevant. I want to pause my question 1 second because somebody raised their hand. Because this is a Zoom webinar, Alexis, I'm gonna pause my question, Alexis, and hit allow to talk. Maybe you're able to talk on microphone. If not, I'll go ahead and put it in chat. So let's try this.
Yeah, but I think you have to unmute me. Can you hear me?
No,
yes,
we can hear you.
Okay, cool. Thanks. I didn't mean you to pose your question. I was just curious about how Ricardo goes about debugging his probabilistic modeling workflows, because I usually end up stuck somewhere and I ask questions on the Discourse and sometimes he answers them. But for me, it's still kind of a big question mark, like how to debug this workflow, because I use also a lot of my own forward models, not like the ones that are straightforward given in PyMC. I create my own solvers and then I use the inference tools. And debugging is a big time costly, and for me a big question mark on how to do it. So any tips would be very welcome.
Yeah, I mean, that's a very broad question. It's a good question. I think everyone has that at some point. Depends a bit on what bugs you're seeing. For instance, if you're seeing just basic stuff, shape bugs I just call prior predictive and just check, do the shapes match of all the intermediate variables. That's usually pretty good to do that. If you have inference issues, which I don't know if it's a bug or a limitation of samplers or whatever, then it's more tricky. Then you have to just probe a bit. So one thing you can do, for instance, if you are sampling with nuts and it's not giving you reasonable things, the first thing you should debug, like, is your log P or your gradients, are they correct? If you are like implementing them yourself, so just test values. And then you can try different samplers. You can try the dumb samplers, the dumber ones like Metropolis, see if they do better. That also means there might be some geometry issues. But in general, I mean, we don't even have a guide. We should have a guide, like how to zoom in on your debugging experience. But it really depends what kind of bug you're getting.
Sorry to jump in. I'm always asking about inference problems. So choosing a solver. I usually don't have gradients, so I end up using something like MT-Dream or SMC. But yeah, choosing the right tool and getting the thing to converge, it's really tricky for me, at least. Yeah, a tool or a guideline would be great. At least I know that every situation is different. But yeah, some suggestions, like high-level suggestions on what to do would be a good start.
So when I have So I guess my workflow, maybe that's better than trying to answer all the problems, is I try to start with a very simple model, the simplest I can, and I do fake data, so I know what are the real parameters, and I just make sure that the sampler can recover the parameters. This already allows me to kind of map the space of maybe it's a data issue, I don't have enough data, or when I have some specific data points, it just goes a wire because specific data points can be problematic. And I guess the best is to just iterate smaller, like add complexity to your model and do again parameter recovery with some kind of data size versus data content, and see at which point the things start to break, which is just I guess it's the probabilistic way of debugging your program step by step. You have to just do some simulations enough to take away the randomness, so you can kind of find out where the problems are. But possibly you're already doing this, so then the best is to share your model, because then it becomes the specifics start to matter.
Yeah, that's great. Yeah, I was actually doing something in those lines, but usually work with synthetic data to start with and try to recover those. And then I'm in the earth sciences, so I have usually noisy and incomplete data to infer from anyhow. But thanks, that was good input.
So what you're doing is what I would recommend. Just can be frustrating and can be slow sometimes, definitely. Also I think many folks recommend this on the stand side. Don't be afraid to just reduce tuning and the number of draws a lot when you are just debugging. Sometimes people wait 5 minutes to find out, if the model they don't care about with the data they don't care about is converging. Part of this is just making it faster can allow you to just solve it more painlessly. Sequential Monte Carlo is different. Actually, not many folks have, I think, using it like in practice. So it's very cool to know you are doing it, and if you can share on the Discourse, it will be pretty nice. Because I worked on the sequential Monte Carlo 2-3 years ago. It was kind of how I started with PyMC. I did the Google Summer of Code, exactly working with simulator, with sequential Monte Carlo and simulator.
Yeah, I worked with it. I'm not sure it was a successful trial, but I can share something on the Discourse. Yeah,
Please do.
It's very valuable.
Yes, for a lot of folks. All right, we are loading up questions now, so I'm gonna move on to the next one. Thank you, Alexis, as well, for both sharing your situation and the common pain that a lot of people have, including me. So good to know at least other people are in it with us. All right, Ricardo, I'm gonna switch over to a question from, I'm gonna hopefully say the name correctly, Catalin. So it's a longer one, and I think you can read it. Can you read the Q&A? You have access to that?
Yes.
Okay, I'm going to read it out loud so it's in the recording. Catalin asks, using PyMC to do Bayesian optimal inference on multivariate distributed random variable. In my use case, I sum 2 beta functions and then use the sum to draw episodes of values. For example, the bias of a warp coin. The question is how does PyMC handles me giving it ground latent to distribution and testing it on a single set of observations, 10 coin flips from some coin bias, versus not providing the latent, giving me many tens of thousands of samples to learn the latent. My use case is actually the first, but I'm a bit worried that PyMC is not set up for the simpler case.
So, yeah, I have to unpack a bit the question. Summing the variables, does it mean you are are you actually observing the sum of 2 beta distributions? I'm assuming beta function means beta distribution, which would sum up the probabilities, or are you summing up Bernoulli trials, which are very different, right? So you're just observing the success or the failure.
And it says, yes, we draw the coin from some multivariate latent.
Okay, so I guess it's a multivariate beta distribution, which I guess is a Dirichlet.
So I think I'm going to take a stab at answering this question, and I would say, I'm gonna try and take a stab at it, and then you let me know whether I got the answer right, Ricardo. What I think is usually like what you said earlier is just write the data generating process in NumPy, and then just use NumPy, just take samples and ensure that that is correct, and then with that you just try and translate it to PyMC. And I've done this myself, right? That way you don't have to deal with all of the Theano and shape. Well, you have to deal with shape uses a little bit, but you don't get. You get a chance to try it out in a simpler form first and make sure that you're getting the values that you think you should be expecting. And then ideally it's easy as then putting PM dot in front of everything and giving it names and then a sampler, and you're good to go. So that, I guess, can I have the same question for you? I would suggest first putting this in NumPy, seeing if it all works there, and then giving it a shot in PyMC.
Yeah, and that also helps a lot because if you share, like if you have a problem in your model and you share it on Discourse and you have your data generating process, I would say the chances that someone is going to find out what's the issue. So sometimes it's a conceptual issue. What you are writing is not what you want to write. It's easier, but also the very simple thing that this is just not equivalent to this in PyMC. It's also, someone will just know that to be very easy. But sometimes the exercise of just writing the simulator is enough to figure out what you actually, I think it's like giving a shape to the model. Yeah. There's a interesting question, but I just wanted to take a tiny step back yes. So just to give a view why I think the probability inference that we do is interesting is in relation to the idea of thinking about Bayesian models as a data generating process, is that it allows you supposedly to, I generate some process, and the last thing I care about is some deterministic operation on some random variables. Maybe I just exponentiate my latent stuff, which in a PyMC model, the way you would write it, that exponentiation operation would be a deterministic usually if you want to sample this to be in the trace. And the cool thing with the automatic inference is that you can say, actually, I can observe, I want to observe, or I want to give as the conditioning data the exponentiation operation, which sometimes, if you're exponentiating a normal, you could just have written as a log normal, but users may not know that, but you could be exponentiating something else, maybe the result of a bit or a transposition or whatever. And the idea is that it doesn't matter to the extent that we have actually wrote the functionality. You can say, this is my model, this is how I generate my data, and this point here is I want to provide the data I actually got from my experiment and do inference. And you don't have to, know, for instance, that if you exponentiate a normal, you get a log normal, or some things that don't even have a standard distribution name, a bit with the same way that you shouldn't have to know the 25 frequentist, tests, if you just understand what they are assuming under the null hypothesis, and you can kind of simulate that process. Just wanted to say that because it was in the back of my mind. Yeah. I was
going to say, I'm glad folks like you are figuring this out, because now I know that if you exponentiate a normal that you get a log normal, but I was like this, and I'm like 4 years into my PyMC journey, and I didn't realize that for the first 3 years. So I just, this is why I'm so glad that this automatic stuff exists. We actually have a lot of questions now. I'm really excited. So we're probably, Ricardo, how much time do you have? You got another 15 minutes?
I can go. Yeah, I can go.
Okay. We're gonna slam through these. I'll just answer one of these. Catalan also asked, I noticed that 2,000 samples for this problem doesn't seem to get me close to the closed form solution. Is there a rule of thumb? There is not a really good rule of thumb. Like Ricardo said, you run a small number of samples and you see if things are getting close, but if they're not converging, then you have to dive into the realm of MCMC diagnostics and traces and checking why your thing is not converging. And there's a whole thread about posterior geometry and hierarchical models, where if you don't do things a specific way, you end up getting biased answers. So I know that was both a really fast answer and a non-answer, but that's a whole can of worms. That's like a whole PyMC talk in itself of how to check MCMC convergence. What I would suggest is just get your sampler running, and then run it for a really long time, and then see where the results sort of taper off. And then that is one okay-ish way to do it, but then after that, there's a bunch of other more statistically precise things you can do. I don't know. Do you have a quick answer to this one, Ricardo?
Well, so when I said you don't need a lot of samples, I was talking in this framework of go back and start with the simplest model. Like if your model just has an intercept, I can guarantee it will fit anything. It doesn't matter how you generate your data. If it has a mean, you can model your model as just having a mean, and you don't need 2,000 samples for the sampler to find out what the mean is, right? So if you are with dumb models, just to find where it breaks, you really don't need to spend a lot of time. There's a pointer where you have your model is fancy and maybe it really works, but you need to tune. If that's your case, you will know when you get there because you have tried all the other things and the simpler ones work like this.
Awesome. All right, let's go to the question from Javier. When improving Bayesian models, reparameterization can solve many issues. Besides central versus non-centered, which I think you mean centered versus non-centered, are there other general reparameterizations? Where can we learn more about it?
Yeah, so there are infinitely many. So that's why I suggested knowing at least Metropolis Hastings, how it works. It's good because many of the reparameterizations you just, how can I let my sample free in a way that is not going to find some edge or some cases where it's going to have to do many rejections, or in the case of nuts, it's going to have to take many tiny steps to not jump off. And many reparameterizations you just playing with kind of your model in a way that the visible outcome is still the same, but the way, the hidden variables, the way they are combined to produce a visible outcome is different, and it can be easier to sample. So one quick example of this, other than the centered, non-centered, is right now, if you use a PyMC Gaussian random walk, and this is not an observed variable, you are, for now, we're going to solve this because I'm saying it out loud now, and we don't want the problem to be there for long.
You're committed to this.
This is not optimal. So right now it's not optimal to use a Gaussian random walk, which we create for users so it's easy to specify one as a non-observed variable, because it's written in a way where the sampler is going to have to propose the right time series. But you can write it, if you're not sampling, you can write it in terms of innovations, where the sampler just has to say, innovate +1, -1, +1, -1, and you don't have to know the whole trajectory. And that's much easier to sample. Or basically, you can just define your Gaussian random walk as a bunch of normals and then take the cumulative sum of them. And that's more efficient than the way it's written now, where the sampler has to think on the space of the cumulative sum already, right? So, and this is just a concrete example of many parameterization is just about letting the sampler work on an easier space that after you do some transformation becomes mathematically equivalent to maybe the other way you had initially.
And when this is, this will dive a little bit into the next question. So, I want to ask this question as well, because I'm learning, to be quite frank. When you're like, and also just so folks know, Ricardo had helped me implement the initial Gaussian random walk over the course of like 4 months. Not Ricardo's fault, more of my learning. So I'm actually really interested to hear this, how this is going to improve as well. Are you gonna modify the PyMC code to use the more efficient parameterization, or is it something in PyTensor where the PyTensor graph is automatically going to compile it?
We're probably going to do it on the PyMC space. So the idea is many variables or many distributions, you want a different form, whether they are observed, meaning the values are static, you're not sampling anything, or you are sampling them. The time series is a clear one where if it's observed, then you have to just work on the data that was given. But if you are sampling, you can work on this latent representation of a time series.
Got it.
But ideally, we don't want users to have to call different functions or tell in advance where something is going to be observed or not.
Yeah.
So we will probably do it as a kind of a model transformation before sampling starts.
Okay.
This is some things that we are exploring in PyMC Experimental, our repository for experimental features. And this is probably where it's going to land first. Because there are many of these where if it's observed, you want a specific form. If it's not observed, you want to reparameterize. But for instance, if you want to do posterior predictive or prior predictive, it's still the same, doesn't matter. And we don't want the users to have to juggle the kind of different shapes or not shapes, flavors of the same thing, just so that behaves better in one context than the other.
Got it. Well, I actually want to take one moment here while you're talking about this show, folks. So let me share my screen, and then we'll get to the next question because it's going to help. Let's share my second desktop. So for folks who don't know, over time we've sort of the PyMC stack has grown. PyMC 3 used to be based on Theano, and Theano was developed by other people. But in the last couple of years, we still maintain PyMC, which you can think of as the modeling interface, and we do a lot of work here, and you can help add distributions and all that here. But we also have PyTensor, which a lot of this automatic probability occurs in as well. So this is now the new backend for PyMC v5, and you can already see Ricardo's name right up here, showing that he made a commit to a merge in main 2 days ago. And so we'll call it the main stack. But then we also have PyMC experimental, where folks like Ricardo and others are putting in some of these new features that we're testing out that we could go one of two ways. So if you're interested at all in any of these ideas or the code or what Ricardo is showing, it's like 99% likely to going to be in one of those 3 repos, both for you to look at, but also to contribute to. So feel free at any point to jump in, ask questions, things like that. We just absolutely love, contributions and help, and for users to see what's going on below the hood. So that's my quick, commercial break for PyMC. It also then goes into the next question, which Daniel asks, are these automatic probability features Ricardo's showing unique to PyMC? Would something like Stan have these features as well?
Well, they are definitely not unique to PyMC. Stan doesn't have. So it's funny, actually. A lot of, from browsing sometimes the Stan forums, a lot of things that showed up there is confusion about, do I need to add the Jacobian for my transformation or not? That kind of never show up in PyMC, because in PyMC you define your model based on, again, the random graph. And in Stan, you actually define it on the log P side, on the probability side. And because you define it on the random side, for us, it's always, there's never an ambiguity when do we want to add Jacobians or not. We add Jacobians when you have a transform, or when you ask PyMC to infer the probability for you, PyMC will know to get the probability correct for this kind of graph, I need a Jacobian term here, here, there, right? When you have to apply the change of variables. So yeah, I mean, depends on the use, right? So Stan doesn't do any inference about probabilities. You have to write the whole, likelihood or whatever. And the PyMC is trying to do this, but it's not unique. So there's other libraries that do this. Even, TensorFlow probability does it a bit, the way it allows you to chain the transformations and then ask the probability. That's just one way of inferring, which is just a simple one of change of variables. Other libraries that do it. I think, how is it? Oryx, which is a new JAX-based PPL, is doing something with this flavor. But it's so, I mean, the functionality is not novel, but it's finding its way to be useful in PPLs. That's something that's being built too. In PyMC, the way we want users to benefit from this is, indeed, if you have a observed process and it's not something that's a standard distribution in PyMC, you should just write the random graph with PyMC variables, put those inside a custom distribution, custom dist like I showed in the end of the talk, and let PyMC infer the log P for you. And this is and we like this because many, different, you can then play very well with distributions because, if you, instead of a Gaussian random walk, you just want a student random walk, you know that wherever you had a normal distribution in your kind of generative process, the way you define your random walk, you just have to swap it by a student distribution, and you don't have to rewrite the log P or anything like that because it will work. It's the same logic PyMC had to use to figure out the Gaussian random walk, it figures out the student random walk. And the cool thing I think about this, and which is a bit also something that's more annoying in Stan, is the idea is you define the random graph, which allows you for 2/3 of the Bayesian workflow. prior predictive, posterior predictive. So
Yeah.
you got those off the bat. And the inference, which is done based on probability, is also done automatically by PyMC. So we infer the probability for your graph. We put the samplers that we think are going to work nicely. And this is going to cover 99% of the cases, of course. Eventually, things will break and you'll have to play directly on the probability side. So you might have to start adding potentials or thinking about transformations or even custom samplers. Yeah. But so that's the idea. So you write the random graph, you get 2/3 of the Bayesian workflow, and we automatically infer the probability. So we give you the third one for free.
Wow.
That's kind of the big picture of what PyMC tries to do as a PPL, I think.
It's a good spelling. All right, we have 2 more questions, and then we'll call it. I think Layla has a question. I have the same question in the vein of Alexis. I'm debugging code, trying to manipulate the chains in order to start draws after warm-up with particular values. Am I missing a simple method, or is this not possible? And then the follow-up after that is a bit more. Essentially, even after touching jitter parameters and trying to set init values, the init state is reset during warm-up.
Let me just see. Trying to manipulate the chain. So the problem is you cannot just, I mean, depends on the sampler. So some samplers you cannot just say, actually, let's say you were here, because they were tuning in a way that has to kind of respect the actual history of the process. With Metropolis, you can. So to answer your specific question, I would have to know which sampler you're trying to mess with. I would say that's a bit of a part of the PyMC ecosystem that we have to clean a bit, which the samplers are really hidden from the user. So it's not easy. Even simpler things like just save the state so you can resume sampling later, something folks have been asking for quite a while. It's not so easy the way we've written those samplers. But we are thinking about it. We don't have specific proposals yet. But we have, for instance, our new experimental nut sampler, which is NutPy, which is one of the projects that Ravin showed there but didn't highlight. For instance, makes it much more straightforward to just, for instance, change the data and resume sampling without having to redefine the model. And it's pretty fast. So we are trying to make sampler both faster to translate across models and also very likely to make it easier to debug and to save and resume, which is a part of, I would say that playing with chains right now would probably, you have to be aware of many hidden variables and states that might be dangerous.
All right. Thank you for that question. And then we have
yeah, sample umpire nuts might be,
it's
more functionally written.
Yeah, and we're also, I think, let me know if my information is out of date, but we're still refactoring and figuring out that whole umpire jacks numpire nut. So the API and the functionality there is changing pretty rapidly. I think it's a more rapidly changing sampler than some of our other ones. Great. Then our last question, which is, I love this one, is W. Dean asks on Discourse, great and super cool talk. Excited to see more transforms, PyMC experimental features, log P support down the line. What functionality is Ricardo looking forward to the most?
Oh, I love that question. Maybe let me share the screen and I'll show you they are already on the way.
Okay.
Not by me, actually, but I will show you folks.
Maybe a sneak peek. Even I honestly haven't seen this either, so I'm quite excited.
All right. Oh, by the way, this is the diagram that I think Ravin was talking about.
Yeah, yes.
So, one is in PyMC. So on the probability inference, I'm really excited about 2 projects that are being done, not by me, by 2 folks, interns in PyMC, Dhruvanshu and Shreyas, on separate projects. So one of them is inferring kind of ordering operations, like taking the max of a bunch of random variables or the mean or just sorting them and inferring the probability for these. It's a bit of an edge case, but there are some very interesting applications. And actually there's an issue where you can follow this. Let me see. Yeah, if you want to see anything for log prob inference, you can look for the log prob related. And yes, so Derovanchu open an issue to track the progress of deriving, for instance, the max and the minimum probability, maximum minimum of different variables. So the idea is we want to infer the probability, the max of 3 uniform variables, which appears in some kind of modeling context where you care about like this is called order statistics. So that's one I'm very excited about on the probability inference. The other one is encoding, so which is a form of censoring where you say maybe values, there's a latent variable, and if the variable is between 0 and 2, you encode this as a 1. If it's between 2 and 4, you encode this as a 2, and whatever. And this, we are also looking for automatically infer the probability of the graphs that kind of represent an encoding process. And if you heard the call or you've seen or used the PyMC sensor distribution, that's a kind of encoding where you have anything below the lower encoding point is encoded as the lower bound, but you could just have encoded it as A or 0. Anything above the upper bound is encoded as another number, in this case, the upper bound. So you cannot really know what was the specific value. You only know all the values marked as the upper bound. They could have been anywhere above, and everything in between stays the same. And what we want is this arbitrary encoding. So you can say anything in whatever subset of bounds can be encoded in a specific way. Other things can stay the same. And I just think it's pretty cool. And you can follow this. So this is issue 6534, no, 6354, which Shreyas, which is another of our summer interns for this year, is working on. So the idea is that you can define kind of a graph where you have a switch based on a variable, and then you get encoded as number 1 or number 2, depending on the value of the variable. And you want to ask then what's the probability of observing either first encode or second encoding. And then you can nest this. So that's what I'm excited for, the probability inference. And on PyMC experimental, now that you asked, I'm very excited about some functionality we've been doing about automatic marginalization. Oops, my headphone fell out of excitement. Automatic marginalization of discrete variables, which is using a bit of the automatic inference we're doing, and it's using a bit of marginalization that, as I mentioned in the talk, we still don't know exactly how we want to offer this to users. But anyway, it's there. So PyMC experimental, I think we already have some documentation, even though, yeah, maybe it's actually good documentation already. So just wait for this to load. If you go to the API reference, it's called marginal model, which is it's a subclass of PyMC model that has one magical method called marginalize, and allows you to you define your model, which can have discrete variables, and then you just say, I want to marginalize this specific discrete variable, for instance, this Bernoulli variable, and then you can sample this model as if the variable was not there, and do just use net sampler with all the continuous parameters that are left. And we want to add some methods like recover the marginalized variable after sampling, or stuff like that. And also allow to marginalize more variables. Right now, you can only marginalize finite discrete variables, and specifically only Bernoulli categorical discrete uniform. We want to allow at least like the truncated discrete versions, like truncated Poisson, truncated binomial, which we can still know which become finite distributions again. So that's something I'm very excited about. So marginal model, try it out. And the other one, maybe, but there's going to be a blog post soon. So we implemented some causal inference with do and observe operators. You can play with them if you know about this, but you're going to have a blog post soon on the PyMC Labs website. But yeah, great question. Many things I'm excited about. And really, folks, the best way you can contribute or help us out is to try it out, because everything in PyMC experimental is like, we have the ideas, but they haven't been battle tested. And they can become really useful by being tested and finding out even if they work, this is limited in this way or that, and that feedback can really help the design.
Awesome. Well, thank you for many things, Ricardo. I mean, most immediately, thank you for the talk on automatic probability and sharing all your knowledge here. And your work on PyMC. And I have to personally say, folks, Ricardo has jumped on many hour plus long debugging sessions with me explaining PyTensor or various parts of the time series modules or things like that. So me personally as well, thank you so much, Ricardo, for your one-on-one expertise and kindness and patience. So,
Of course.
folks, this is a running web series. We are actually hot. Within the next couple of days, we're going to publish the next event from Max about soccer factors model. You'll see his interview published within the next week. We're getting fantastic help from Poorna, who's also on this call, coordinating this also. Everyone be sure to thank Poorna as well. But we will be sharing Max's interview soon. His notebook will come up in the next couple of weeks so you can get a handle on his code. And then he will be doing a live session around July 17th, sometime around that week. So you know where to find the meetup threads and discourse threads and everything like that. I will also point out PyMCon is a rolling CFP. So if you ever want to be Ricardo and you want to come up here and talk about something cool that you're doing that you want to share with the community to inspire people, just go to pymccon.com/CFP, publish or share your proposal idea, and then internally we vote on it and accept the next talks. So thank you again, both Ricardo and everybody that showed up. I hope to see you async online, publishing lots of code and pull requests and things like that. And we will see you at the next one.
Thanks.